Welcome. Over the course of the upcoming 30 minutes, I will be talking about data-based methods for spatial audio reproduction. Data-based spatial audio scene representations are those in which the spatial information is embedded in the audio signals. These are opposed to model-based scene representations, which are essentially composed of a set of source signals like speech or music, as well as metadata that describe, for example, the positions of the sources, the geometry of their environment, as well as physical models that represent the radiation properties of the sources that the scene is composed of. Data-based scene representations obviously have to be recorded with microphone arrays. This can be also in the form of dummy heads, in which case the spatial information is embedded in the binaural signals that the dummy head captures. Under label B, you see a 4-element microphone array that is embedded in a Microsoft Kinect device, which is an accessory for a gaming console. Label C are some compact circular microphone arrays, and labels D and E then represent simple or more advanced ambisonics compatible microphone arrays. Obviously, any model-based representation can be turned into a data-based one simply by sending it through a virtual microphone array. The other way around, turning a data-based scene representation into a model-based one, is a little trickier. When it comes to the rendering, there's no difference between model-based, no essential difference between model-based and data-based. Eventually, some rendering has to turn the scene representation into loudspeaker signals, and these loudspeakers can either be mounted into a pair of headphones or they can be mounted as part of an array that is placed somewhere in a room. In this presentation, I will review the literature on data-based methods in spatial audio with a particular emphasis on the role that machine learning plays in this context. In a way, the present presentation can be understood as an overview and inventory over what is available. Plus, of course, we will also perform some categorization and also reflection on what we found. By the way, some of the methods that we will be referring to here, they work based on continuous signal streams. Other work primarily or exclusively on impulse response representations. We will not differentiate explicitly between the two categories because conceptually they are identical. The presentation is based on an article manuscript entitled "A Review of Machine Learning and Other Data-Based Methods for Spatial Audio Capture, Processing and Reproduction," which co-workers and I submitted to the EURASIP Journal on Audio, Speech and Music Processing. It is still under review currently. It is fairly extensive. It has more than 20 pages and features more than 200 references, including pointers to existing overview articles on different sub-aspects of data-based spatial audio. So please excuse that we can only point out a small selection of reference in this presentation. Appended to this video will be the entire reference list of the articles of the article manuscript. So you can see that this article has more than myself as the author. Particularly, it is authored by Maximo Cobos of Universitat de Valencia in Spain, Konrad Kowalczyk of HRTF University of Science and Technology in Krakow, Poland, as well as Archontis Politis of Tampere University in Tampere, Finland. My name is Jens Ahrens and I am based at Chalmers University of Technology in the Swedish town of Gothenburg. So here we go. The presentation will be organized based on the general structure of the spatial audio processing pipeline, which consists in a capture stage that captures the spatial audio scene, then converts it into some sort of abstract signal-based representation that is either directly piped into the reproduction stage, or there is an optional processing stage in which, for example, information is extracted from the sound scene or the spatial information in the sound scene is manipulated. The output format of the processing stage can be the exact same one, like the input format, but it can also be a different one. Typical representations that are being used are either raw microphone signals, raw signals from the microphones in an array, or mathematical representations like plane wave decomposition or spherical harmonic decomposition, which is also known as ambisonics representation. The ultimate scene representation that serves all purposes in the an ideal way has not been available yet, so that certain methods work only based on certain scene representations, and other methods work only based on other scene representations. One could say that the ultimate goal of the capture stage or processing stage, if one would like to formulate it that way, is to decompose a data-based scene in all its elementary components, that is the individual source signals, their positions, the different components of the reverberation, and thereby essentially turn it into a model-based representation that can then be manipulated arbitrarily. We are far away from this. This is why it rather may be seen as a very, very far ahead long-term goal. Most capture methods rely on the underlying physics of, say, the capture hardware or the arrangement, the physical relation between the signal channels of a microphone array, which are well understood, and there are powerful mathematical tools available. So there's not much room for machine learning here. This is different when it comes to feature-based representations. Feature learning or representation learning is typically understood as a set of techniques that allow machine learning algorithms to automatically identify favorable representations from the input data that can efficiently encode the information that is needed for performing a given task. This feature learning process may be supervised when labeled data are used, or it may be unsupervised when no labeled data are needed or available. Such abstract, intangible, machine-identified feature representations are not available in spatial audio yet. What is available are so-called handcrafted features, and that have been used successfully for certain tasks. Such handcrafted features can be the phase differences or the correlation between the channels of a microphone array, for example. Such representations then can be used for machine learning-based source localization or machine learning-based sound source separation. Another category of feature-based representations operate based on binaural signals. Machine learning-based methods have been successfully used, for example, to identify auditory localization cues or perform source localization or the like, based on binaural signals for single or even multiple sources. We also found a study that showed that the elevation localization cues that were identified by a convolutional neural network are comparable to those that were identified by humans in the psychoacoustic literature. Finally, machine learning has been used on binaural signals to identify the scene composition with respect to foreground and background, for example, or the relative position of the user in the scene. And this has sometimes even happened with an accuracy that is higher than what humans are capable of achieving. So let's move on to the processing stage of the pipeline. The processing stage typically either extracts desired information from the output of the capture stage, or it manipulates the spatial information. During our literature search, we've identified three major categories of methods. One is the methods that analyze the captured sound field to extract, for example, acoustical parameters like reverberation time and the like. Then we have found a set of methods that manipulate spatial information in the captured scene. And finally, there are methods that perform joint processing of audio and visual information, whereby the visual information is typically available as a video that accompanies the audio signal. You will find that our tree also comprises a branch on source localization, detection and separation and the like. I'd like to skip these methods at this point As we will see in the discussion that concludes this presentation, such methods are more closely related to other application domains of machine learning, like image processing, for example, rather than actual spatial audio, so that it is more convenient to discuss the methods then. Let's start with the methods for acoustic analysis. The literature on conventional signal processing in this context is vast and most likely well known to all of you. So I'm going to focus on machine learning based solutions here. Deep neural networks, they have been used for the computation of scattering, another wave phenomena, or for the reconstruction of the geometry of an object from the scattered field, or even for reconstruction of the geometry of a room based on microphone signals. Room reverberation has also been predicted, for example, mostly from visual data. Then we also see sound field reconstruction based on machine learning methods from a small number of irregularly spaced microphones. So we move on to the category of sound scene processing, in which the spatial information of a sound scene is manipulated, usually by decomposing the scene into perceptually meaningful components. The analysis and decomposition branch is dominated by machine learning, and as I stated previously, I'll comment on those shortly in the discussion. The analysis and synthesis branch is clearly dominated by conventional signal processing. It is certainly fair to say that spatial impulse response rendering, proposed by Mary Ma and Pulki in the early 2000s, is a stepping stone in the parameterization of sound fields. Spatial impulse response rendering separates the direct sound in a B-format room impulse response from the diffuse part per frequency bin. This has been very successful and has inspired a whole set of methods which include directional audio coding, Dirac, higher angular resolution plane wave decomposition, HARPEX, the coding and multidirectional parameterization of ambisonic sound scenes, COMPASS, and many more even. Spatial audio coding is prominently applied in the MPEG context by means of conventional signal processing. So similarly to sound field parameterization, the sound scene is decomposed into objects of different perceptual salience. Audio upmixing refers essentially to converting a sound scene representation into one with a higher number of channels, which usually comes with an apparent increase of the spatial resolution. The sound field parameterization methods that I discussed just now, they provide this functionality inherently, but there are also dedicated methods available for this based on conventional signal processing. Deep neural networks have been employed in this context rather recently, and primarily for the extraction of ambience. Dominating are still the conventional signal processing methods. Lastly, viewpoint translation, that is applied particularly in the context of binaural reproduction, gained momentum recently, and it performs a viewpoint translation either by means of manipulating a spherical harmonic representation of a sound scene, which is obtained from a single microphone array recording, or by cleverly parameterizing and interpolating between array recordings that were performed at different locations. All this is based on conventional signal processing. Finally, in the processing stage of the pipeline is audio-visual processing. So here we're back in the domain of machine learning. Videos, they have been used based on machine learning to support source localization, for example, speaker recognition, speaker separation, and the like. Then spatial alignment of 360-degree videos obtained from YouTube that featured the exact same scene, but were recorded from different view angles, has also been performed. And information that was extracted from a video stream has been used to turn monophonic audio recordings into stereo recordings, or even Ambisonic's B format. So spatial information that was extracted from the video was imposed onto an otherwise non-spatial audio signal. So let's move on to the reproduction stage of the processing pipeline. The reproduction stage mostly uses linear methods with more or less of a physics-based motivation. So, for example, wave field synthesis, ambisonics-like methods, stereophony, binaural reproduction, and the like. There is not much room for machine learning here. The exception in this context is the synthesis, selection, and the individualization of head-related transfer functions, HRTFs. As you are all aware, HRTFs are highly individual and the measurement is resource intensive. It's therefore desirable to select a most favorable HRTF set from a given pool of HRTF sets, or to even generate the HRTFs from scratch based on the anthropometric features of the listener. This is then all usually done using machine learning. Traditionally, principal component analysis has been used for dimensionality reduction of HRTF data. It has also been shown how HRTFs can be synthesized based on sparse combination of a subject's anthropometric features, for example. HRTF selection, with the help of deep neural networks, usually uses some sort of psychoacoustic data. This has been shown to yield better results than when using instrumental error measures like spectral distance or the like. In this case, it was such that subjects listened to program material to assess the fitness of different HRTF sets by assigning a given score based on which the neural network was then driven. Machine learning has, of course, also been employed in the generation and synthesis of HRTFs. Here, it can get fairly involved, as several networks, including autoencoders and like, are combined, and it gets so involved that I don't even dare to comment on more details here. Please refer to the article that accompanies the presentation once it is available. A valuable byproduct of the HRTF generation and synthesis is the circumstance that these methods actually can interpolate HRTFs too. Either way, whenever machine learning is employed, large data sets are required for this to work. So we have covered the entire spatial audio pipeline and have summarized the most important bits of it, so that we're now ready to discuss what we have observed. Many of the paradigms in spatial audio are deeply rooted in physics. It has unfortunately been clear since quite some time that perfect physical accuracy of the signals, for example, that are delivered to the ears of a listener, would require immense resources, if it is possible at all. Just think about how many microphones you would require in a spherical microphone array for it to be able to obtain a physically accurate sphericomonic representation of the impinging sound field over the entire frequency range. Physical accuracy, it can be desired because it guarantees the best possible perceptual result. This result may not be perfect because, as you are aware, there's more to spatial audio perception than just the signals at the ears. There is, of course, the visual impression, but also less tangible aspects like the awareness of the listener of the situation, as well as the expectations of the listener. Yet, it has been proven that authenticity, that is a synthetic experience that is indistinguishable from a natural template, that this can be achieved with only moderate physical accuracy. This means essentially that different ear signals can lead to the exact same perception, so that perfect physical accuracy is not even required. The capture and reproduction stages base heavily on the underlying physics, and powerful mathematical tools are available. The non-machine learning based approaches in the processing stage, they use perceptually motivated representations of acoustic scenes to accurately reproduce the relevant spatial cues. That is, they create signals such that they may be different from the perfect ear signal, but still lead to the exact same perception. And they do this while preserving the highest audio signal fidelity. That is, they minimize any processing artifacts. Many of these data-based techniques, including parametric processing, upmixing, spatial audio coding, viewpoint translations, and the like, they successfully achieve their designated goals without employing any machine learning. So as a consequence, these methods have been playing a dominant role in spatial audio and multimedia applications. The major breakthroughs of machine learning have been taking place particularly in image processing. The methods there that were successful there have been quickly adopted in related audio processing tasks. Image separation, for example, it assigns a label to each pixel of a digital image. Similarly, acoustic source separation can be understood as an analogous task of labeling time frequency bins in a spectrum. Another example is image classification, which corresponds to scene classification in audio. Spatial audio tasks like foreground-background classification or HRTF personalization may also belong to this category of methods that is closely related to those that were successfully established in image processing. And machine learning has been very successful also in the audio applications here. Also, machine learning has been successful in all spatial audio tasks for which a mathematical model of the task is difficult to establish or not available at all. Typical example is the audiovisual processing, where spatial information is extracted from a video and imposed onto an audio signal. So machine learning has been very successful here. There are, though, many spatial audio tasks for which machine learning based methods are either not available at all, or they are lagging behind in their performance compared to conventional signal processing methods. So why is it such? Well, spatial audio tasks are very complex in that they require the joint control of spatial features, timbre, and the signal fidelity. And there is no end-to-end mathematical model for all of this. Physical accuracy would be much easier to define by means of mean squared error and the like, but modeling a desired psychoacoustic result on a signal level is incomparably harder. Here are three examples of compilations that may be considered to summarize the state of the art in the psychoacoustic modeling on a signal basis. When studying those, but there's of course much more literature on this, but we would like to use these three examples here. When studying this literature, you will find that there are mathematical or computer models that can predict spatial perception from ear signals, for example, mostly only for very simple scenarios, or if the scenarios are more complex, then it is a narrow range of scenarios that can be handled. Richard Lyon's book on human and machine hearing, for example, together with other comparable literature, targets rather non-spatial applications in the modeling, such as music information retrieval and the like. Using machine learning speak, one would say that the difficulty lies in the definition of the loss function. The loss function or objective function is the function that is being optimized during the learning state, during the training of a neural network based on following its gradient. The loss function has an important job in that it must faithfully distill all aspects of the model down into a single number in such a way that improvements in that number, they are a sign for a better model, for an advancement in the training. I would like to highlight the significance of the loss function with a quote from the book Neural Smithing, Supervised Learning in Feed-Forward Artificial Neural Networks by Russell Reed, which may be considered a little outdated, yet the quote still applies in the exact same manner today. Quote on, "It is important, therefore, that the function faithfully represents our design goals. If we choose a poor error function and obtain unsatisfactory results, the fault is ours for badly specifying the goal of the search. Quote off. So if machine learning fails in a specific task, it is not machine learning to be blamed, but rather the person that operated the machine learning method. Another obvious and fundamental limitation in the development of the machine learning methods is the availability or the lack of large data sets for training, as well as the associated data volume with those data sets if they are available. Multi-channel audio data can simply overwhelm the available cache memory or computation power. Here's an example. The popular Vox Celeb2 dataset, which is used for speaker recognition, it contains about 1 million utterances, so a fairly high number, and thereby has a duration of 2,000 hours, which corresponds to a data volume of just below 80 gigabytes. This is something that can be handled with computation resources that are available to many researchers in the world. In comparison, the dataset, the B format, so 4-channel dataset that is associated with the DCASE 2021 challenge on sound event localization and detection, has a duration of only 20 hours, but comprises already almost 14 gigabytes. So the duration is a factor of 100 lower, but the required sampling rate is higher and there's more channels. So imagine an according higher order ambisonics database, and we're talking again 1, 2, or even 3 orders of magnitude of larger data volume. And then we are in a range that requires computational resources that are available only to very few people in this world. By the way, our EURASIP article manuscript on which this presentation is based, it presents a couple of pointers that we collected to available data sets that are relevant in this context. So, in summary, machine learning has surpassed conventional signal processing in selected tasks in spatial audio. Yet the performance of conventional signal processing and all the human cleverness in the models behind it is far ahead of machine learning in other tasks. The degree to which machine learning-based spatial audio methods will be successful in the future will largely depend on how the audio research community addresses the discussed challenges, and on the emergence of new applications possible only with machine learning. For the time being, we are still waiting for the appearance of further disruptive machine learning-based methods and applications that can deliver spatial audio processing that is out of reach today. Thank you very much.